There's a measurement in astronomy that breaks something fundamental in your brain, and once you see it, you can't unsee it. It's called the light year. You've heard it 1,000 times. In documentaries, textbooks, casual conversations about space, it rolls off the tongue like an everyday unit. But there's something wrong with it, something that doesn't fit, something that quietly exposes a crack in the way your mind was built to understand the world. And tonight, we're going to step into that crack. You already understand distance without thinking about it. You navigate it every single day. A kilometer is a 10-minute walk, the kind you take to clear your head or grab coffee. You know how it feels in your legs, how long it takes, how the scenery shifts as you move. 5 kilometers is an errand across town. 20 kilometers is a drive with a few songs playing on the radio. 100 kilometers fits neatly into an afternoon trip, windows down, the world sliding past in familiar rhythms. These distances live inside you. They're woven into your memory, stored in the architecture of your brain as patterns you've walked, driven, felt 1,000 times before. Your mind treats them like old friends. Even when you scale up, the numbers still cooperate. 1,000 kilometers is a day's drive. 5,000 kilometers is a cross-country journey. The kind where you watch mountains rise on the horizon or deserts stretch endlessly beneath a burning sky. You can imagine it. You can picture the meals, the stops, the slow accumulation of distance. It still makes sense. And then there's Earth itself, 40,000 kilometers around the equator. Enormous, yes, but not incomprehensible. You can imagine explorers tracing its outline with wooden ships over years. You can imagine jetliners circling it in less than 2 days. It's a sphere you could, in theory, walk around if your life were long enough and your patience infinite. The planet is vast, but it doesn't defy understanding. It still echoes with human experience. This is the world your brain was designed for, not metaphorically, literally. Your neural architecture evolved in landscapes measured in meters and kilometers, not light years. Depth perception developed so your ancestors could judge the distance to a piece of fruit or the length of a jump. Spatial processing evolved to navigate forests, plains, coastlines, environments where the farthest visible point might be 10, maybe 20 kilometers away on a clear day. Research shows that your brain doesn't even process space the way you think it does. The posterior parietal cortex handles nearby space, the kind you can reach and touch. The anterior regions handle navigational space, the kind you walk through. But there's a limit. Your brain processes room-sized to building-sized environments in systematic gradients, with different neural regions specializing in different scales. Beyond a few kilometers, the system starts to improvise. It wasn't built for anything larger. Your ancestors never needed it to be, but the moment you leave Earth's surface, something unravels. Look up. The moon, bright, familiar, close enough that it feels like you could almost reach it with a long enough ladder. And yet, its true distance, 384,000 kilometers, lands in your mind like a word from a foreign language. You can say it, you can write it, but you can't feel it. There's no memory, no experience, no comparison your brain can make that turns that number into something you truly understand. The reason is simple. Nothing in your life has ever been that far away. Not the horizon, not the mountains, not the farthest city you visited. Nothing your species has touched, hunted, gathered, or imagined for the vast majority of its existence comes even close to the distance to the moon. When the Apollo astronauts traveled there, they crossed a void your brain has no equipment to measure. They moved at 11 kilometers per second. In one heartbeat, they traveled farther than you walk in a morning. In a single minute, They covered more ground than an hour-long drive. And still, even at that astonishing speed, they drifted toward the moon for 3 full days. Think about that contrast. Immense speed, immense time, and the result is a kind of cognitive failure. Your intuition collapses. You know the astronauts were moving fast, you know the moon is far. But the two ideas refuse to connect into a single picture. The scale simply doesn't fit inside the space your brain has available, and the moon is close. Cosmically speaking, it's right next door. Now consider the sun, 150 million kilometers away. At this scale, kilometers become flimsy, almost meaningless. You can multiply the number. You can write it down. You can compare it to other numbers. But it never becomes a picture. Your intuition gives up entirely. The sheer volume of zeros drowns out comprehension. And yet, the sunlight warming your face right now began its journey 8 minutes ago. 8 minutes before it reached you, it left the surface of the sun and raced across the emptiness of space at the fastest speed anything can travel. When you watch the sunrise, you're not seeing the sun as it is. You're seeing it as it was. 8 minutes in the past, painted onto the present by the unavoidable delay of light. Everything you see in the sky is delayed. The moon's light takes just over a second to arrive. The sun's takes 8 minutes. Nothing you observe out there is happening now. You're always watching the past, dressed up as the present, because light, even moving at 300,000 kilometers per second, still needs time to cross the gulf of space. This is where distance stops being something your senses can navigate and becomes something purely abstract. A number on a page, a concept you calculate with but cannot visualize. And then you encounter the light year, 9.46 trillion kilometers. In miles, that's 5.88 trillion. Either way, the number is so large it might as well be infinite. To put it in perspective, a light year is the equivalent of about 32,000 round trips between Earth and the Sun. It's the distance light, moving at the ultimate cosmic speed limit, travels in an entire year of uninterrupted motion. No pauses, no slowing. 300,000 kilometers, every single second for 365 days. Consider Voyager 1, the farthest human-made object from Earth. Launched in 1977, it's been traveling for nearly 50 years at tens of thousands of kilometers per hour, every day without stopping. It has crossed the boundary of our solar system and entered interstellar space. It is farther from home than anything humanity has ever sent. And after all that time, all that speed, all that distance, Voyager 1 is only about 1 light day away, 1 day of light's travel, not even close to a light year. If you wanted to reach the nearest star, Proxima Centauri, at Voyager's current speed, you'd need to wait 70,000 years. Or consider this. The space shuttle, one of the fastest vehicles humans ever built, would take 370 centuries to cover a single light year, 37,000 years of continuous flight at full speed just to reach a distance that light crosses in one orbit around the sun. The glitch starts to reveal itself here. When you hear light year, your brain instinctively hears the word year and treats it like time, like something you can wait through, like a duration. But it's not. It's distance. Pure, incomprehensible, almost meaningless distance, measured by how far the fastest thing in the universe can run before exhaustion that never comes. And this creates a strange dissonance. The light year feels like it should be graspable. It has a name. It appears in sentences. But when you try to hold it in your mind, it slips away. You can't picture it. You can't map it against anything you know. It exists in a realm your brain was never designed to enter. This isn't a failure of education or imagination. It's a limitation built into your neural hardware. Human perception evolved to prioritize quick assessments over precise measurements. Your ancestors needed to judge whether a predator was 10 meters away or 20. They needed to know if a river was narrow enough to cross or too wide to risk. They didn't need to conceptualize distances measured in trillions of kilometers. There was no evolutionary pressure to develop that capacity. Recent research has revealed something even more striking. Your brain's spatial processing doesn't expand linearly, it expands hyperbolically. Studies from 2022 show that neural representations of space actually conform to hyperbolic geometry, a curved non-Euclidean structure where distances grow exponentially as you move away from a reference point. Your brain literally distorts space to fit it into manageable chunks. It's an elegant solution for navigating forests and cities, but it means the universe, which follows flat Euclidean rules at large scales, doesn't match your brain's architecture. You're trying to map an infinite cosmos onto hardware designed for a few square kilometers, and the light year exposes that mismatch. It's a unit that exists in the universe's language, not yours. It measures distances your species was never meant to feel, across voids your ancestors never imagined, at speeds your intuition cannot hold. But here's where it gets stranger. The light year isn't just a unit that breaks your intuition. It's a measurement that reveals something deeply wrong about reality itself, something Einstein discovered that still haunts physics today. Every speed you've ever experienced, every car, plane, or rocket, is a rounding error compared to light. And that's not even the strange part. The fastest car you've ever been in probably topped out around 120 kilometers per hour on a highway. A commercial jet flies at roughly 900 kilometers per hour. The International Space Station orbits at about 28,000 kilometers per hour, fast enough that astronauts see 16 sunrises every day. These speeds feel extreme. They push against your sense of what motion should feel like. But light moves at 299,792,458 meters per second. Let that number sit for a moment. Not kilometers per hour, meters per second. In a single second, light crosses the width of Earth 7.5 times. In the time it takes you to blink, light has already traveled farther than some spacecraft journey in an entire year. In 1 nanosecond, 1 billionth of a second, light travels exactly 1 foot. This is why radar works. Engineers measure the time it takes for a radio pulse to bounce back and calculate distance based on light speed. 1 foot per nanosecond, precise, unwavering, absolute. And here's what makes it truly strange. That number isn't measured anymore. It's defined. In 1983, scientists fixed the speed of light as an exact constant and redefined the meter around it. The meter is now defined as the distance light travels in 1,299,792,458 of a second. Light speed isn't derived from measurement. It's the measurement. It's the ruler by which everything else is judged. This wasn't always obvious. For most of human history, people assumed light moved instantly. You opened your eyes and you saw? No delay, no travel time, just immediate connection between you and the world. But in 1676, a Danish astronomer named Ole Romer was studying Jupiter's moons when he noticed something peculiar. The eclipses of Io, one of Jupiter's largest moons, happened earlier or later than expected depending on where Earth was in its orbit. When Earth was closer to Jupiter, the eclipses appeared ahead of schedule. When Earth was farther away, they were delayed. Romer realized the timing wasn't off because Jupiter was misbehaving. It was off because light took time to cross the changing distance between Earth and Jupiter. This was the first experimental proof that light had a finite speed. It didn't arrive instantly, it traveled, like sound, but unimaginably faster. Over the next 2 centuries, scientists refined the measurement. By 1838, Friedrich Bessel succeeded in measuring the distance to a star for the first time. The star, 61 Cygni, was so far away that its light took 10.3 years to reach Earth. Space, it turned out, wasn't measured in kilometers or miles. It was measured by how long light needed to cross it. Distance became time. Time became distance, and light became the ruler that united them both. But the real strangeness didn't emerge until Einstein. In 1905, Einstein published a paper that quietly broke physics. At its core was one deceptively simple idea: the speed of light is constant for all observers, no matter how fast they're moving. It sounds innocent, almost boring. But when you follow that idea to its logical conclusion, reality starts to crack. Here's the paradox. Imagine a spaceship moving at half the speed of light, 0.5 c. The crew turns on their headlights. Intuition says the light from those headlights should travel at 1.5 times the speed of light relative to someone standing still, because the ship's speed and the light's speed should add together. That's how speeds work in everyday life. If you throw a ball forward from a moving train, its speed relative to the ground is the train's speed plus your throw. But that's not what happens with light. The light from the spaceship's headlights doesn't travel at 1.5 c. It travels at exactly c, 299,792,458 meters per second, no matter who measures it. The person on the ship measures it at c. The person standing still outside the ship also measures it at c. Somehow, impossibly, light moves at the same speed for everyone. To make this work, to preserve the constancy of light's speed, something else has to give, and what gives is space and time themselves. They warp, they bend, they adjust to keep light's speed absolute. This is time dilation. The faster you move, the slower your clock ticks relative to someone standing still. It's not an illusion. It's not a trick of perception. It's a physical, measurable effect embedded in the structure of space-time. In 1971, scientists tested this directly. They took atomic clocks, devices so precise they lose less than a second over millions of years, and flew them around the world on commercial airplanes. When the clocks returned and were compared to identical clocks that had remained on the ground, they showed a measurable difference. The flying clocks had aged less, only by a few hundred nanoseconds, but measurably, undeniably less. Time had literally passed more slowly for them. This isn't just a laboratory curiosity, it's something engineers deal with every single day. GPS satellites orbit Earth at speeds fast enough and far enough from Earth's gravity that their onboard clocks tick differently than clocks on the ground. Specifically, they gain about 38 microseconds per day compared to Earth-based clocks. That might sound tiny, but GPS calculates your position based on the time it takes signals to reach you from multiple satellites. If engineers didn't correct for relativistic time dilation, your GPS would drift kilometers off course within hours. Your phone's navigation works because engineers account for Einstein's equations. Reality forces them to, and it happens to people too. Astronaut Scott Kelly spent nearly a year aboard the International Space Station, moving at 28,000 kilometers per hour. When he returned to Earth and scientists compared his biological clock to his twin brother Mark, who had remained on the ground, Scott had aged 5 milliseconds less. 5 milliseconds out of an entire year, barely measurable, but real. Time moves slower for him because he was moving faster. This leads to an even darker truth. Nothing with mass can ever reach the speed of light. It's not a matter of building better engines or finding more efficient fuel. It's a structural feature of space-time itself. The closer you push toward light speed, the more reality pushes back. Time slows, space contracts along your direction of motion, and your mass effectively increases. The energy required to accelerate you grows exponentially. To reach exactly the speed of light would require infinite energy. The universe simply doesn't permit it. We see this directly in particle accelerators. Scientists routinely accelerate subatomic particles to 99.99999% of the speed of light. At these speeds, the particles live longer than they should. Particles that normally decay in microseconds survive for milliseconds because, from their perspective, time has slowed to a crawl. This isn't speculation, it's measured in laboratories every day. The particles age more slowly because they're moving faster. Time dilation isn't a theory. It's an observed fact of nature. The closer you get to light speed, the more pronounced the effects become. At 90% of light speed, time slows to about 44% of its normal rate. At 99%, it drops to 14%. At 99.999%, it slows to a fraction of a percent. You could cross vast distances in what feels like days, while centuries pass for the rest of the universe. And this is the ultimate barrier. Not an engineering challenge, not a technological hurdle. A law carved into the fabric of existence. Light moves at the maximum speed anything can move, and the universe enforces that limit by warping space and time around anything that tries to approach it. Now imagine an astronaut embarking on an interstellar journey. She boards a ship capable of traveling at 95% of the speed of light, an impossible achievement by today's standards. But let's imagine it's real. Her destination is a star 9.5 light years away. At 95% of light speed, the journey takes just over 10 years from Earth's perspective. But for her, inside the ship, time moves differently. 10 years on Earth compresses into about 3.1 years of her experienced time. She arrives at the distant star still young, still sharp, still carrying memories of the world she left only 3 years ago. She turns around and makes the return journey. Another 10 years pass on Earth, another 3.1 years for her. When she steps off the ship, 20 years have passed on Earth. She has aged only about 6 years. Her family has grown older. Her friends have moved on. The world has changed in ways she can barely recognize. She didn't travel through space, she traveled through time. And the light year, that innocent-sounding unit of distance, was the mechanism that exiled her from her own present. This isn't science fiction. It's not a thought experiment. It's verified, measured, inescapable physics. Time is not universal. It bends, stretches, and warps depending on how fast you move and how deep you sit in a gravitational field. And the light year, by forcing you to move at relativistic speeds to cross it in any reasonable time, guarantees that distance and time can never be separated. So light travels at the ultimate speed limit, and time itself bends to accommodate it. But that creates an even darker problem, one that turns every star you see into a kind of ghost.